In this lecture, we continue our discussion on the critical path method. In the previous lecture, we introduced the critical path problem on the network by considering this example. The network or the project network comprises of a set of activities, and there are some precedence relationships among these activities. Based on these precedence relationships, we were able to draw this network, and the procedure to draw was explained in the previous lecture. Now, after drawing this network and after writing down the durations associated with each activity, we would now like to find out when earliest this project can be completed. Now, to do that, we followed a labeling procedure which was also described in the previous lecture, but we go through that procedure once again to understand a few more aspects. Now, let us assume we start here with time equal to 0. Now, this takes a duration of 15, so we reach this at 15. This takes a duration of 20, so we reach this at 20. Now, when we come here, this we reach at 15 plus 10, 25, 20 plus 15, 35. Now, this node 4 represents the point at which both D and E are completed, and therefore, the maximum of the values would be the label for the node, and we would get 35 here. Now, when we come to 5, this indicates the completion of both C and G. So, it is 15 plus 25, 40, 35 plus 20, 55. The maximum of that is 55. Similarly, 35 plus 15 is 50, 20 plus 20 is 40, the maximum is 50. And for 7, 55 plus 10, 65, 35 plus 30, 65, 50 plus 20 is 70. So, based on this labeling procedure, we say that the earliest it takes to complete this project, to complete all the activities along with the given precedence and the duration, is 70 units of time. Now, the labeling procedure was very similar to the Dijkstra's algorithm for the shortest path problem, except that the node label here was the maximum of the times as against the minimum of the times that we considered when we solved the shortest path problem. This labeling is a forward pass of the labeling procedure. We also go through a backward pass of the labeling procedure. So, we start with the same 70 here, but we use a different symbol, a circle for example, and then go through the backward pass. So, this is 70 minus 20, which will be 50, 70 minus 10, which will be 60. So, when it comes to 4, this will become 70 minus 30, which is 40, 50 minus 15, which is 35, and 55 minus 20, which is 35. So, we choose the minimum of them and we get 35 for this. For this, it is 55 minus 25, which is 30, 35 minus 10, which is 25. So, we take the minimum of this. For this, it is 35 minus 15, which is 20, 50 minus 20, which is 30, the minimum was 20, and for this 25 minus 15, 10, 20 minus 20, 0, minimum is 0. So, we have completed the backward pass also associated with this, and when we started the backward pass with this number 70 and we proceeded backwards, we were able to get 0, which was this. Now, when we look at both the labels that we have drawn, the forward pass label, which is shown inside a square and a different color, and the backward pass label, which is shown inside a circle and of a different color, we realize that some nodes have the same values of the labels, like for example, node 1, node 3, whereas some nodes have different values for the labels like node 2 and node 5. We also observe that if we have a path, we are able to get a path that starts from 1 and ends with 7 in this network, such that all the vertices in the path have equal values of the forward pass label and the backward pass label. And such a path, if you see carefully, is the path 1 to 3, 3 to 4, 4 to 6 and 6 to 7. So, this path, which is 1 to 2, 1 to 3, 3 to 4, 4 to 6, 6 to 7 with length equal to 70, which is 20 plus 15 35 plus 15 50 plus 20 70, is the longest path, and it is also called the critical path of this network. So, the critical path is the path that goes from the first node to the last node, such that all the vertices that are there in the critical path have both labels equal. Now, the other paths in this network, for example, 1 to 2, 2 to 5, 5 to 7, or 1 to 2, 2 to 4, 4 to 7, other paths that are there will have length less than or equal to that of the critical path, and if they are equal, then they become alternate critical path, but if they are strictly less, those paths are not critical. So, all the paths from 1 to 7 are either critical or non-critical, and all non-critical paths will have length less than that of the critical path. For example, 1 to 2, 2 to 5, 5 to 7 would now have 15 plus 25, 40 plus 10, 50, which is less than this 70, which is the critical path. So, we also understand that the critical path is extremely important in this network, and for this network to be completed at time equal to 70, then we have to do these activities sequentially, and some of these activities, the non-critical activities, or those that are not in the critical path, can have some more extra time, and they can be fitted in such that the total project duration stays at 70. We also understand that if there is a delay in these critical paths, by which it takes more than say 20 units of time, say 21, then the length will become 71 and the time to complete the project will increase. So, to that extent the critical path is extremely important, and this labeling algorithm would help us get the critical path. Now, we also need to look at one more thing. What does this thing indicate? Now, here there is a difference, there is a 15 and a 25, here there is a 55 and a 60 and so on. So, there are nodes where the forward pass label and the backward pass labels are different, and do they convey something? What do they convey? Now, we try and define something like this here, that if we take the forward pass, the box in the forward pass the thing that is shown in this forward, the box represents what is called the early start of that particular activity, and whatever is shown in the backward pass represents the finish or late finish of that activity j. Now, we start defining some terms here, and we start defining a couple of terms. Let us find out, for example, for a particular arc ij, for an arc ij or for an activity ij, let us define the backward arc quantity, the backward pass quantity j minus forward pass quantity I minus dij, and let us also define the forward pass quantity j minus forward pass quantity I minus dij. For example, if we take this activity C, if we take this activity C, say for activity C, now this is this quantity which is 60, which is activity C is 2 to 5. So, the backward pass label for J is the label corresponding to 5, which is 60. The forward pass label is the label corresponding to this, which is 15, minus the duration, which is 25. So, this will be 60 minus 15 is 45, minus 25 is 20. Now, the second one is 55 minus 15 minus 25, which is 15. Now, what do these two numbers tell us? Now, what it tells us is, if we look at this activity C, the earliest this can start is 15, the latest this can finish is 60, its duration is 25. So, there is a certain, it can start, it cannot start before 15 and it should end at 60, which means there is a 45 duration period in which this activity, which takes 25 units, has to be completed. If this activity, it cannot start before 15, and if it is scheduled in such a way that it ends after 60, then the critical path will be affected. But within this buffer time of 45 time units, 25 is the duration that is required for this. So, there is an excess buffer of 20 that is available for this. So, this 20 is called the total float associated with that activity. So, for this activity there is a float, total float of 20. Earliest start is 15, so earliest finish is 40, so latest finish is 60. Therefore, there is a float associated with this. That float is 20 units of duration that can be consumed. For example, if we look at this, the earliest it can start is 55, the earliest it can finish is 65. So, there is a float of 5 associated with this. Now, the next thing is called a free float. The earliest it can start is 15, the earliest it should finish is 55. So, 15 plus 25, 40 plus 15, which is 55. This is called free float. Now, both these total float and free float in some sense tell us the excess time that is available, and by the way these numbers are written down, the free float is always less than or equal to the total float. While the total float tries to tell us the excess buffer or total buffer which can be used, which is 20, somewhere 15 can be used comfortably for this, so that, and if it stretches beyond 15, it will still try and affect something somewhere. So, both these floats give us a picture of some extra time that is available, and total float represents some kind of an extra time that is available across the entire path containing these arcs, and free floats are specific to the arcs. Nevertheless, without going very deep into the meaning of these two, we can understand that both these floats in a certain manner represent the extra time that is available, which has to be used, and any poor scheduling by which this exceeds the floats that are available for that activity, then this activity will become critical. So, this is how the longest path on the network is computed. The critical path is the longest path in the network, and the critical path computation is quite similar to the Dijkstra's label, except that instead of labeling the minimum, we label the maximum. Now, we need to show and understand why this kind of a labeling is optimal for this problem, for which we write a linear programming formulation and try to understand the primal dual relationships and show that indeed this forward pass would give us the longest path on this network. So, to that extent, the CPM that we are looking at in this lecture series can be seen as an application of linear programming technique to solve real life project management problems. So, let us first write down the primal and then the dual and try to understand how this labeling is optimal. So, as always we are interested in finding the longest path in this network. So, the xij equal to 1 if ij is in the longest path equal to 0 otherwise. So, the objective function will be to maximize sigma Cij Xij, where Cij stands for these durations. Now, this is the origin. So, the longest path should start from here. Therefore, we have the usual x12 plus x13 equal to 1. As far as node 2 is concerned, we have minus x12 plus x24 plus x25 equal to 0. 2 being an intermediate node, if the longest path goes through this, then 1 comes here. So, one of which has to be 1. If it does not go through, everything will be 0. So, you have simply a flow balancing or conservation equation for every intermediate node. Now, for 3 we would have minus x13 plus x34 plus x36 equal to 0. For 4 we have minus x24 minus x34 plus x45 plus x46 plus x47 equal to 0. For 5 we have minus x25 minus x45 plus x57 equal to 0. For 6 we have minus x36 minus x46 plus x67 equal to 0, and for 7, which is the end node, we have minus x57 minus x47 minus x67 is equal to minus 1, because the longest path should end at 7. So, we get minus x47 minus x57 minus x67 is equal to minus 1. So, these are the equations for this. Then we have xij equal to 0 1. This formulation is very similar to the shortest path formulation, except that the shortest path will have a minimized Cij Xij. Here we have a maximized Cij Xij. We have already seen that the shortest path problem is unimodular, and unimodularity has only to do with the constraints and it has nothing to do with the objective function. So, the longest path problem, the way it is represented on this kind of a network where you have arcs from I to j, j greater than I, is unimodular, and therefore, we can treat this xij to be greater than or equal to 0 and solve the resultant linear programming problem, which would give us the optimal solution to this. Now, having understood that this is a linear programming problem, we will now go back and write the dual associated with this problem. So, we define dual variables W1, W2, W3, 4, 5, 6, 7. The primal is a maximization problem. So, the dual will be a minimization problem, minimize W1 minus W7 that we have here, subject to every ij will be in the ith and the jth constraint. So, subject to W1 minus W2, it is a maximization problem with all greater than or equal to constraint. So, you will get a minimization problem with all greater than or equal to variable. So, W1 minus W2 is greater than or equal to 15, W1 minus W3 is greater than or equal to 20, W2 minus W4 is greater than or equal to 10, W2 minus W5 is greater than or equal to 25, W3 minus W4 is greater than or equal to 15, W3 minus W6 is greater than or equal to 20, W4 minus W5 is greater than or equal to 20, W4 minus W6 is greater than or equal to 15, W4 minus W7 is greater than or equal to 30, W5 minus W7 is greater than or equal to 10, W6 minus W7 is greater than or equal to 20, and importantly all the Wj's are unrestricted in sign. The unrestricted comes because of these equations. Now we make another interesting change here, that because these Wj's are unrestricted in sign, we are now going to replace each Wj by say minus Wj dash, and because Wj is unrestricted, minus Wj dash will also be unrestricted in sign. So this will now be rewritten as minimize W7 dash minus W1 dash, which will become minimize W7 dash minus W1 dash subject to W2 dash minus W1 dash greater than or equal to 15, W3 dash minus W1 dash is greater than or equal to 20, W4 dash minus W2 dash greater than or equal to 10, W5 dash minus W2 dash greater than or equal to 25, W3 dash minus W4 dash greater than or equal to 15, this is W4 dash minus W3 dash is greater than or equal to 15, W6 dash minus W3 dash greater than or equal to 20, W5 dash minus W4 dash greater than or equal to 20, W6 dash minus W4 dash greater than or equal to 15, W7 dash minus W4 dash greater than or equal to 30, W7 dash minus W5 dash greater than or equal to 10, and W7 dash minus W6 dash greater than or equal to 20, Wj dash unrestricted in sign. Please remember that because we have replaced Wj by Wj dash, this will become minus W1 dash plus W2 is greater than or equal to 15. Remember, we are not multiplying this equation by minus 1, the right hand side will remain the same, we are only replacing the variable Wj by minus Wj dash, so that this becomes minus W1 dash plus W2 dash, it will still be greater than or equal to 15. So we now have this as the dual which comes from this, and now we can start with W1 dash equal to 0. Now when W1 dash is equal to 0, automatically W2 dash is greater than or equal to 15, and we want to minimize somewhere W7 dash minus W1 dash. So W2 dash will become 15, W3 dash will become 20. Now from this W4 dash will become 15 plus 10 25, and W4 dash is 20 plus 15 35. So W4 dash is greater than or equal to 25, W4 dash is greater than or equal to 35, so W4 dash will become equal to 35. Now for W5 dash you get 25 plus 15, so greater than or equal to 40, this is greater than or equal to 55, so W5 dash will become 55. For W6 dash you get 20 plus 20 40, and then 35 plus 15 50, so W6 dash will become 50, and W7 dash will become, this is 30 plus 35 65, this is 55 plus 10 65 plus 20 70. So starting with W1 dash equal to 0, we can go through this set, and by inspection we can get a solution here with 70. Now we go back and find out, apply complementary slackness and see which are the ones that are satisfied as an equation. So this is satisfied as an equation, this is satisfied as an equation, then W4 dash comes from 15 plus 20, W4 dash comes from 15 plus 20, this is an equation, W5 dash comes from 35 plus 20, 55, so this is an equation, W6 dash comes from 35 plus 15, 50, and W7 dash comes from 50 plus 20, 70. Now from these we have fixed W1 equal to 0, so 6 of them give us the equations. So now apply complementary slackness, wherever it is satisfied as an equation, the corresponding variable is a basic variable. So x12 is a basic variable, x12 is a basic variable, x13 is a basic variable, x34 is a basic variable, x45 is a basic variable, x45 is a basic variable, x46 is a basic variable, and x67 is a basic variable. So these are the 6 basic variables that we have, and then we realize that the solution will be x12 plus x13 equal to 1. So now we treat x13 equal to 1, x12 equal to 0. So this is satisfied. Now from this x12 is basic, so 0 equal to 0, from this constraint it is satisfied. These are non-basic, this is a basic variable, but these are non-basic at 0, this is a basic variable at 0, so you get 0 equal to 0. As far as this constraint is concerned, x13 is equal to 1, so this contributes a minus 1, therefore x34 will be equal to plus 1, so that this is satisfied. As far as this is concerned, here x34 has 1, so this is contributing a minus 1, then we have 4 5 is 0, 4 6 is 1, so x45 is 0, x46 equal to 1, so that minus 1 plus 0 plus 1 is 0, x45 is a basic variable with 0. Now this is a basic variable, so we get 0 equal to 0, these two are non-basic. Now x46 equal to 1 would give us x67 equal to 1, because you have a minus sign here, so you get x67 equal to 1. Now as far as this is concerned, x67 is 1, so minus 1 equal to minus 1. So we have a set of 6 basic variables which correspond to these 6 equations coming from this solution. These 6 are satisfied as equations, so these 6 are the basic variables, and with this set of basic variables we are able to get a basic feasible solution which satisfies this set, which satisfies the primal, and we could get degenerate in situations like here we get 0 equal to 0, and somewhere here also we get 0 equal to 0. Otherwise it is a degenerate basic feasible solution which is obtained by applying complementary slackness from here. The objective function value associated with this is 1 3, 3 4, 4 6 and 6 7, which would give us 70. So we have a dual feasible solution, we have applied complementary slackness, we have got a corresponding primal feasible solution with the same value of the objective function. Therefore it is optimal to both the primal and the dual respectively. Now this also shows that whatever we computed as 0, 15, 20, 35, 55, 50, 70 are the labels that we have here, 0, 15, 20, 35, 55, 50 and 70. So when we write the dual, so the algorithm that we developed here, which was actually the modification where we updated the largest value instead of the smallest, is optimal to this particular problem. So wherever we write the primal and the dual, and when we make this change and then we can start with W1 equal to 0, we will get the forward pass labels. On the other hand, if we used this and if we started with W7 equal to 0 or 70 as the case may be, we could come back and get the backward pass labels. In fact, if you remember very carefully, we did a very similar analysis for the shortest path problem. We also mentioned that we could write the dual this way, and then we mentioned that if we write the dual this way, we get the forward pass, whereas if we write the dual this way and move from W7 equal to 0 or 70, we would get the backward pass labels. So, this is the relationship between the primal and dual of the longest path problem. The critical path problem can always be formulated as the longest path, and a simple forward pass and a backward pass of the Dijkstra's algorithm suitably modified for the longest path would give optimal under these circumstances. The circumstances are very important. The network is made up of arcs such that arcs go from I to j, j greater than I. If we are able to do that, then this problem can be formulated as a longest path problem, and this particular longest path problem can be solved optimally using a polynomially bounded algorithm whose optimality can be proved by the primal dual relationships that we have shown here. So, this is how we solve the longest path problem. Now, there are a couple of other things that we might see in the longest path, in the critical path problem, and one of the things that is very common, which we will also do for the sake of completion, is trying to analyze the critical path, particularly when the durations are non-deterministic. Now, when we did the critical path, we have assumed that these durations are known and deterministic. Now, there could be situations where these cannot be estimated accurately. So, they will follow certain distributions. So, whenever they cannot be estimated accurately, then it is customary to look at distributions, and instead of fitting a distribution, it is also customary to fit 3 estimates of the demand, which is called the optimistic estimate, the most likely estimate, and the pessimistic estimate. Now, these are usually called as A, M and B respectively for every one of these activities. So, it is obvious that M is greater than or equal to A and B is greater than or equal to M, because the pessimistic estimate is higher than that. Now, these kind of estimates are drawn for each of these activities, and then the mean time is calculated assuming a beta distribution as A plus 4m plus B by 6, and the variance is given by B minus A by 6 the whole square. Now, based on this distribution, now the expected value and the variance are computed, and now each of these will have an expected value and the variance. Now, with these expected values, one can substitute these with the expected values and then do one pass of the CPM or the critical path method to get the estimated or expected longest path, and along with that the duration will be the expected duration. Now, since variance is additive, we could add the variances and say that this is the expected critical path with a certain expected variance. So, the analysis shifts from a purely deterministic analysis here to more of a probabilistic analysis, and such a thing is called PERT, which is called program evaluation and review technique. It is called program evaluation and review technique. Now, this technique represents a probabilistic analysis. One can also do certain simulations of these networks to also try and find out the expected longest paths, but those things are slightly beyond the scope of this lecture series. So, we are not proceeding in that direction. We only wish to inform that these problems are close to the OR problems that we have looked at, and while the CPM, the critical path method, can be treated or seen as an OR application of finding the longest path on a particular type of a network, PERT offers a probabilistic analysis of the network. We will see one more aspect of the critical path problem before we complete our discussion on it. Now, when we come back to the critical path method, we characterized each activity by its duration. There will be situations where certain resources are required to carry out these activities. For example, if this is from a construction project network, of course, we need material, we need people, etc. And many times we will not have an unlimited number of these resources. So, we will be constrained by resources, and that leads to what are called resource constrained project scheduling problem. Resource constrained project scheduling problem. We could have single resource, we could have multiple resource and so on. Just to give an example, if we are looking at material as a resource, or if you are looking at labor as a resource, people as a resource. Now, this will become for activity A, we could say 15 and 2, which means 2 people are required to carry out this 15. Now, for example, if we say B would mean 20 and 3, which means 3 people are required to carry out B. And then if we have a restriction that we have only 4 people available, then we cannot do A and B parallelly, because to do them parallelly we require 5 people. And because we cannot do them parallelly, the longest path in the network will increase, and the earliest time that we can complete a project will also increase. So, the resource constrained project scheduling problem will now become a very similar formulation of the CPM problem plus resource constraints. In fact, the actual formulation of the resource constrained project scheduling problem will be slightly different from what we show here, but in principle it will be the longest path problem with resource constraints. So, the moment we add the resource constraints into the problem will lose its unimodular structure, and the problem now cannot be solved as a linear programming problem. The problem will become an integer programming problem. It becomes a very hard problem, and it becomes an application of integer programming, a topic that we have covered in this lecture series. So, there are popular branch and bound algorithms as well as heuristic algorithms to solve the hard problem, which is the resource constraint project scheduling problem. However, the normal critical path problem, which does not include the resource constraint, or to state that this assumes that an infinite amount of resource is available, so that resource is not a constraint, then that problem becomes the longest path on this network, and it can be solved by an adaptation of the labeling procedure that we applied to solve the shortest path problem. So, this brings us to the end of our discussion on the critical path method, and then we go to the next topic, which is quadratic programming. Now, quadratic programming is a part of non-linear programming, and in this lecture series we will be restricting ourselves to understand only one algorithm to solve the quadratic programming problem. So, before we introduce a quadratic programming problem, we have to introduce a non-linear programming problem and then show where the quadratic programming comes under the general umbrella of non-linear programming or non-linear optimization. We are very comfortable, we have addressed the linear programming problem extensively in this lecture series. So, the linear programming problem now has a linear, it has an objective function which is linear, it has a set of constraints, and all these are linear, and it has an explicit restriction of greater than or equal to for the variables, which is called the non-negativity restriction, and all these three will constitute a linear programming problem. Now, what is a non-linear programming problem? So, if there is a non-linearity in the objective function, or if there is a non-linearity in the constraints, then the problem becomes an NLP or non-linear programming problem. One of the important things in non-linear programming problems is that we do not have the explicit mention of variables to be greater than or equal to 0. The variables can even take negative values at the optimum or at the solution, and if we wish to say that the variables have to be greater than or equal to 0, these become explicit constraints in the NLP instead of being implicitly given as they were given in the linear programming problems. Now, when we have nonlinear functions that we wish to optimize, then we have these classifications. So, we have what are called unconstrained optimization problems, and then we have constrained optimization problems, and these constraints can be equations and or these can be inequalities. We also of course have single variable optimization problems and multiple variable optimization problems. Now, when we solve these type of optimization problems, we have what are called necessary conditions and we have sufficient conditions for optimality. We are quite aware that the first derivative equal to 0 from calculus of a single variable optimization, first derivative equal to 0 would give the optimum, and the second derivative at the optimum will qualify whether it is a maximum or whether it is a minimum. So, let us look at these. So, if we have an unconstrained optimization problem, then we simply have, if it is a single variable, df by dx equal to 0 gives a maximum or a minimum. The second derivative would tell us whether it is a maximum or whether it is a minimum. If we have unconstrained optimization problem with multiple variables, then dou f by dou x equal to 0 would give us the maximum or the minimum, and then the dou square f by dou x square will have to be computed as a matrix. We need to do dou square f by dou x1 square, dou square f by dou x2 square, and so on. So, there are these sufficient conditions for sufficiency for whether it is a minimum or whether it is a maximum. Now, here because we are restricting ourselves to quadratic programming, we are not going to concentrate that much on the sufficiency condition. We are only going to concentrate on trying to get the maximum or the minimum when it actually exists, which means trying to put the first derivative equal to 0 and trying to solve them. So, we first look at just describe an unconstrained optimization problem first without we have seen that, then we start describing constrained optimization problems and then show equations and inequalities and then present a way to solve them and then come back to quadratic programming. Now, let us look at a problem like this. Maximize x1 square plus 2x2 square plus 2x3 square subject to x1 plus x2 plus x3 equal to 5 and x1 plus 3x2 plus 2x3 equal to 9. See, in this example we do not have an explicit mention of x being greater than or equal to 0. Now, if we did not have this constraint, then we would have simply taken the partial derivatives equal to 0 and then we would have got the minimum or the maximum point. First derivative equal to 0 gives the optimum. Of course, if it were unconstrained, then it would only be a minimum and it would not be a maximum. Now, this is a maximization problem with constraints. Now, let us assume that we know to solve this kind of problem when there are no constraints, that is dou f by dou x equal to 0, first derivative equal to 0 gives us the solution. But the moment we have constraints, how do we handle that? So, one of the ways of handling constraints, particularly when the constraints are equations, is to use Lagrangian multipliers Now, take this to the objective function by introducing as many Lagrangian multipliers as the number of constraints. So, in this case we would introduce Lagrangian multipliers lambda 1 and lambda 2. So, this problem will become L, which is the Lagrangian function, will be x1 square plus 2x2 square plus 2x3 square plus minus lambda 1 into x1 plus x2 plus x3 minus 5 minus lambda 2 into x1 plus 3x2 plus 2x3 minus 9. Now, we need to describe why we put a minus for this lambda 1 and lambda 2. Now, the reason is, now we always write this of the form lambda into Ax minus b, where the constraint is of the form Ax equal to b. Now, if we remove this constraint, then it becomes an unconstrained problem, and if we add this constraint, it becomes a constrained problem. So, any time when we add a constraint to a maximization problem, the objective function value comes down, and therefore, we subtract, we put a minus lambda 1 and then write Ax minus b. So, minus lambda 2 to do this. Then we can go back and take partial derivatives equal to 0 would give us the corner point, and then we have to look at the sufficiency condition and verify that whatever we got by the partial derivatives is actually a maximum. So, we just go only up to the partial derivatives. So, you could do dou L by dou x1 equal to 0, dou L by dou x2 equal to 0, dou L by dou lambda 1 equal to 0, dou L by dou lambda 2 equal to 0 would give us the solution. And in this case, we have this the whole thing is now a second degree, a quadratic expression. There is a square, 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 lambda 1 x1 is quadratic, and so on. So, now first derivative of all these would give us linear equations. So, solving these linear equations would give us the corner point associated with the optimum. Then we need to go back and show that the corner point that we obtained is indeed a maximum. So, whenever we have equations, we can use the method of Lagrangian multipliers, introduce as many Lagrangian multipliers, take it into the objective function, and then use a dou L by dou x equal to 0, dou L by dou lambda equal to 0, and solving the resultant system would give us the corner point. Except that we need to know how to solve the resultant system. This whole thing being a quadratic function, all the derivatives would give us a linear equation. Say if this were cubic, then the resultant equation will have a quadratic term, and then we may have to resort to a suitable method to solve such a thing. Nevertheless, Lagrangian multipliers present us with a framework with which we can attempt problems of this size. Now, we get into another situation. What happens when these constraints are inequalities instead of equations? So, when these constraints are inequalities, let us take another problem. So, let us consider a problem like this, which is minimize x1 square plus 2x2 square plus 3x3 square subject to x2 plus x3 greater than or equal to 6, x1 greater than or equal to 2, x2 greater than or equal to 1, and that is it. So, this does not have an explicit restriction that x1, x2 should be greater than or equal to 0. So, when we have this, then we can't directly use the Lagrangian multipliers, because the Lagrangian multiplier method is meant for equations. So, whenever we have inequalities, the first thing that we have to do is to convert these inequalities into equations. So, if we write a general expression that we have here, like if we do in a general maximization problem. So, if we have maximize z is equal to f of x, where this x is variable x1, x2 to xn, subject to g of x less than or equal to 0. Now, g of x less than or equal to 0 has 3 constraints here. It is always possible to multiply this with -1 to convert it into g of x less than or equal to 0. So, this is a general form of a constrained optimization, nonlinear optimization problem, where the constraints are of the inequalities. Now, in linear programming, we are used to saying to write this as, for example, x2 minus x5 equal to 1 and put x5 greater than or equal to 0. Because linear programming has this explicit restriction that every variable is greater than or equal to 0, it was easy to write this as x2 minus x5 equal to 1 and then say x5 greater than or equal to 0. In nonlinear programming, we do not have this explicit thing. So, what we normally do is to convert this as g of x plus s square equal to 0, where we introduce a variable s associated with every constraint, and that s can be negative or positive. Therefore, we write, since this is less than or equal to 0, then we would write g of x minus plus s square is equal to 0. So, this quantity is less than or equal to 0, whether s is positive or negative, s square will always be positive. So, you get g of x plus s square equal to 0. Now, we introduce a Lagrangian multiplier, as many multipliers as the number of constraints here, and then we write maximize L is equal to, or L is equal to, we just set up the Lagrangian function, L is equal to f of x minus lambda into g of x minus s square. So, we already explained why we put a minus for a maximization problem, because a constraint problem will only bring down the value of the objective function. So, we bring this in. This lambda is called the multiplier or a dual variable associated with this. Now, we can apply the principles of optimization to get dou L by dou x equal to 0, dou L by dou lambda equal to 0 and dou L by dou s equal to 0. Now, when we do this, we get this form. Now, dou L by dou x equal to 0 would give us del f of x minus lambda del g of x equal to 0, because this is dou by dou x del f of x. Now, this will not be there because we are partially differentiating with respect to x. So, minus lambda del g of x equal to 0. We would get dou L by dou lambda would give us minus g of x plus s square equal to 0 from here, and dou L by dou s would give us lambda minus 2 times lambda I s I equal to 0. Now, these three are the typically the equations that we get when we partially differentiate L with respect to x, with respect to lambda and with respect to s. Now, we can always write this as lambda greater than or equal to 0 del f x minus lambda del g x equal to 0. Let me write this, lambda I g I of x equal to 0 and g I of x less than or equal to 0. So, we write this as these 4 important things. Now, what are they? What is the relationship between this and this? Now, this is exactly the same as this, there is no problem. Now, g of x plus s square equal to 0 is the same as g of x less than or equal to 0. So, now we write minus 2 lambda I s I equal to 0 is now written as lambda I g I of x equal to 0 and lambda greater than or equal to 0. Now, lambda greater than or equal to 0 comes only then we have this quantity which will reduce the objective function. So, when we put a minus lambda, lambda has to be greater than or equal to 0 for the inequality that we have. So, lambda is greater than or equal to 0. So, the only other thing that we have actually left out is lambda. So, this would tell us either lambda is equal to 0 or S of I equal to 0 or both equal to 0. So, this is lambda greater than or equal to 0. So, when lambda is greater than 0 strictly, then we have when lambda is greater than 0, g of x is equal to 0, and when lambda is 0, then g of x is less than or equal to 0. Therefore, we get lambda I into g I of x equal to 0. So, this is now replaced by lambda greater than 0 and lambda I g I of x equal to 0. This is a general form that we will use to solve problems of this type. Now, these conditions are the very well known Kuhn-Tucker conditions, which form the basis for solving nonlinear optimization problems. Sometimes these are called KKT conditions, Karush-Kuhn-Tucker conditions, but we use the term Kuhn-Tucker conditions for this. So, the Kuhn-Tucker conditions are the actual conditions that we can generalize, and we need not derive this every time. We can simply generalize this, and then for every nonlinear problem which is described in this form, maximize z equal to f of x with g of x less than or equal to 0, we can simply write the Kuhn-Tucker conditions, and depending on the resultant system that we get, we can solve those equations and inequalities. Some of them may be equations, some of them may be inequalities, some of them may have higher degree, which all depends on what happens with this f of x and with this g of x. If f of x is cubic or has a higher power, then del f of x will be quadratic or more, and so same with g of x. So, once we write the Kuhn-Tucker conditions, we simply solve the resultant equations and inequalities to get the maximum or the minimum. Of course, sufficiency will have to follow, but we are not looking at sufficiency in this lecture series. In the next lecture, we will see the application of Kuhn-Tucker conditions to a quadratic programming problem.